We're waiting to see whether these two talk to each other or not. And if they don't, then we have a problem.
So welcome back everybody. Here we'll continue with the topic, internal critiques of materialism within physics, from physical physics to quantum mechanics. Thank you.
Thank you very much. And I hope all of you have had a good cup of coffee, because you could need it. Me too. Perhaps more than anywhere else, it is this afternoon that the meat of this symposium will lie. Then I've kept it all very unmathematical, largely because frankly everyone agrees about the maths, and nobody agrees about what it means. So we're going to try to talk a little bit about what it might mean, and it is particularly important for us. As you remember, this morning we covered briefly what materialism was historically, its Western and Indian backgrounds, the long interview which I have called the faith, and the features of modernity of which we are all the product, of which materialism and realism are key components, as well as what I have called the technological component. And then I mooted a series of arguments, preliminary arguments, as we call them, which put materialism in question. First was the private experience of consciousness, and then we talked of altruism and empathy, of pre-verbal ethical sense, infants, and of the poverty of stimuli argument in linguistics. Then, separately, each of these arguments has a fair bit of weight. When you start taking them together, they have a substantial amount of weight, and they raise a lot of questions. However, as far as materialism and realism are concerned, perhaps no argument has more weight than that of what is known as the status of the observer in quantum mechanics. This is not a theory, it is an established reality in quantum mechanics. The theorems exist. There's a lot of disagreement about their meaning, and there has basically been, since I studied physics, since 35 years ago, a gentleman's agreement in physics. This is something we shall not talk about. So, when you start studying quantum mechanics at university, it's very striking. You do the maths, and if you're good at the maths, and you come to your teacher after the classes, and you ask him, so, this is your question. What exactly does this mean? You've got an entity which can be both a particle and a wave, depending on the intention of the observer. It's a bit odd. And there's no one inside. Your professor will come up with his private theory. And it might be the discontinuity of space, the discontinuity of time, the non-material nature of the phenomenon. But if there's anyone inside, he will tell you, we really don't know. We just do the maths. So this has been going on for more than 80 years. And this is the reason why this morning I wanted to cover with you Thomas Kuhn's understanding of scientific development, the genesis of scientific theories, and the paradigm shift. The example I gave you this morning was drawn from a very classical element of physics, a transition from Newtonian physics to the special theory of relativity, which concerns us literally. But the reason I wanted to cover this with you is because I think with quantum mechanics we are in a period of crisis, and we have been in a period of crisis for more than 80 years. We are in the midst of a shift of paradigm. And basically, the resistance is so great, it's not happening. And this paradigm shift is going to have to occur. You will see that the data is just piling up. So at a certain point, as far as physics is concerned, it's simply going to have to occur. Then the other sciences lag far behind physics, largely because they do not have to address the microscopic biology, to a much lesser degree chemistry. Chemistry does address quantum phenomena. Biology basically does not. So they can afford for the time being to remain on a pre-quantic paradigm. You will find that both biology and chemistry function very much on a Newtonian model. And it is unsurprisingly from biology and chemistry that the sirens of materialism are most to be heard. Dawkins is a biologist, Dennett is a biologist, most of those who are vociferously critical of the non-material nature of consciousness are biologists, and not to put too fine a point on it, they are 1.5 centuries behind the curve. So, well, you have to say things bluntly. And a long time ago, the book was translated in 1983 in English, but it was actually initially written in the 1930s. Fritz London and Bauer were the founders of quantum chemistry, said quite clearly, one can't doubt the possibility of establishing philosophical truths by the methods of physics, but it is surely not outside the competence of physicists to demonstrate that certain statements which pretend to have a philosophical validity do not. And all this afternoon's conference will be dedicated precisely to deconstructing these statements. So, when contemporary biologists quite casually reduce the mind to the brain, and therefore the mind to matter, it has to be pointed out that even within a materialistic context, as Kelly makes it very clear, the advances in physics are so great in the last century that even the reduction of the mind to the brain is not a straightforward statement. Matter is not what we thought it was. It has become glaringly obvious in the last 120 years after, well, first from 1905, Einstein's famous photoelectric paper, where for the first time light was treated as a particle. And then Einstein's famous equation, linking matter and energy. It has become very clear that we don't have a very clear understanding of what matter is. So, even a stark materialist who reduces the mind to the brain is making anything but an obvious statement in the light of contemporary physics. This is something I think biologists may be verbally aware of, but it does not seem to penetrate much deeper than this. And then we will address the gist of our conference, which is quantum physics and the critique of three components of the common sense view of reality: realism, locality, and determinism. And in this respect, I thought Escher's drawing of the hand drawing itself is excellent. It really summarizes the problem of observation in quantum mechanics. The observer observing the phenomenon defines by his observation the observed phenomenon which in turn interacts with you. You have a feedback loop between observer and observed phenomenon. So before entering into the quantum description of reality, we have to move backwards a little bit, and we will keep all of this very unmathematical and philosophical. It makes it more simple for all of us. To classical physics, and to the way classical physics understands causality. And by the way some of the Buddhist schools of philosophy understand causality too. So, in classical physics, for two phenomena, A and B, to be causes, first, they must exist out there. This is the hypothesis of realism. You exist, I'm sure this will shock you, whether I'm in the room or not. And if it doesn't shock you, then you're a very advanced person. That is realism. Then, if two phenomena are causally related, the cause must come before the effect. And they must be spatially contiguous. This is locality. You cannot have, locality is often formulated in very naive terms. You cannot have two phenomena which are hugely removed in distance. So you'd be formulating this in terms of the speed it takes light to connect two phenomena. Hugely removed in distance, which are causally related. This would violate the special theory of relativity. And you need necessary correlation or determinism. Whenever B occurs, A has occurred. So whenever the apple hits the ground, someone dropped the apple. So this is classical causality. And now if we flesh it out a bit, studying the hypotheses of classical physical causality one by one, we can see that if A causes B, you have an observer on the outside of A and B. That's your hypothesis of realism. You have anteriority. A occurs at t0, B occurs at t1. The arrow of time is, if you wish, is unidirectional. You have locality. They are somehow together. It might be a distance of a couple of meters, a distance of a couple of kilometers, but in physics nowadays, they cannot be so far removed that there's a causal relation which occurs faster than the speed of light between these two objects. Right? And finally, there must be necessary correlation. In other words, whenever we observe B, it is certain and definite A has occurred. This is classical physical causality. Now, all of this is going to be turned on its head in approximately half an hour. So you have half an hour to enjoy reality. And then we are all going to get hopelessly confused. I hope I will be able to bring us out of confusion somewhere. Now, quantum mechanics was discovered, I would say, unintentionally, by Max Planck, the last of the great classical physicists. Planck had absolutely no desire, I suppose, to stumble on something as odd as quantum mechanics. He studied a very classical problem in physics, which is known as the black body radiation problem. You take something which is known as a black body, which is basically at a constant level of temperature, and you study the relationship between the temperature of the body and the frequency of the radiation, electromagnetic for instance, if you heat the body to a very high temperature, what we call light, which is radiated. And it's a difficult problem mathematically, but it didn't seem to be anything particularly transcendental in terms of meaning, and it's very interesting because, for instance, all the light bulbs we have in this room basically hinge on the black box effect. So Max Planck was basically hired by the greatest German light bulb company of the period. This is late 1880s, but just nascent, to try to find a way to make more efficient light bulbs. And to try to find a way to make more efficient light bulbs, he figured he had to solve the light bulb problem. What's the relationship between basically heat and radiation, and how much electricity do you have to put in a filament to cause radiation, and radiation of which frequency? Seems quite straightforward. But what Planck found is very disturbing from the standpoint of classical physics, is that in such a black body, the levels of radiation are not continuous. In other words, you don't have a steady stream of radiation. Let's say, imagine, the black body radiates at 1 gigahertz, 1 gigahertz and 1 hertz, 1 gigahertz and 2 hertz, 1 gigahertz and 3 hertz. This doesn't happen. You have jumps to the levels of radiation. This is completely abnormal. There is a theoretical necessity of this analysis. And these jumps are called quantums. So Planck accepted this as just sort of a mathematical trick to try to understand the black body. The black body radiated energy discontinuously. Okay. He didn't attach too much importance to it. And for some 15, 20 years, maybe, Planck did not fully understand the import of his research. It's Einstein in 1905 who understood that this was inherent to the process of radiation of energy. It was not something accidental and extraneous. And this is the beginning of quantum mechanics. This is the first counterintuitive result in quantum mechanics, which contains many. Then, pursuing on Planck's research, one of the most brilliant physicists of the 20th century, Heisenberg, studying the classic atom you always take as an example in quantum mechanics, the hydrogen atom is very simple. There's one proton and one electron. Discovered something even more embarrassing. Generally speaking, if you have a hydrogen atom, this is a depiction of a hydrogen atom, it is in a series of discrete states. So its angular momentum, which is, if you wish to think of it as the rotational component of the electron, it's not far from the truth, is discrete. It does not have all of the states between 0 and 1. It can be either 0 or 1 or 2. And the orbits of the electron are also discrete. They are quarters, in other words, discrete states. But what Heisenberg found, to his great embarrassment, studying the behavior of the hydrogen atom, is what is known as his uncertainty principle. Some of you may have heard about it. For a given particle, let's say an electron, the product of the uncertainty of the position, which is delta x, by the uncertainty of the quantity of movement, which is the speed, if you wish, product of mass by the speed, is necessarily greater than a constant, which is called h over 2p. In other words, if you know delta x with 100% certainty, in other words, delta x is 0, right? You know the position with 100% certainty, delta p becomes infinite. In other words, you have no idea regarding the mass or velocity of the particle. If, on the other hand, you know delta p with 100% certainty, in other words, there's no variation of p, delta p becomes 0, then the position is totally unknown. In other words, you cannot know at the same time, for a subatomic particle, its position and its mass. It is impossible. You can know approximately both. You can know one perfectly and the other not at all, or the opposite. You have, in other words, it would seem, according to Heisenberg's principle, an inherent limit to what we can know. Now, Heisenberg understood this in very pragmatic terms. It seems his understanding was perhaps incomplete. Heisenberg understood this as a statement regarding the experimental means used. That if the experimental means used to understand the position with 100% certainty were applied, those experimental means would hinder the understanding of the quality of motion, the momentum, and the opposite. This was the understanding in the 1930s, and most modern physicists nowadays believe it's a fundamental property of matter. There is an inherent unknowability in matter at the subatomic level. And already in this respect, Heisenberg himself had to acknowledge that quantum physics had moved far away from 19th century physics, very far away indeed. For classical Newtonian physics, you can know, theoretically, in practice you can do the calculations, but theoretically, you can know everything about it. Its position, its quantity of movement, its angular spin, anything you want to know, it's all there in the equations of classical mechanics. According to Heisenberg's principle, there is an inherent limitation to our knowledge at the subatomic level. Fundamental limitation. And as I explained to you, therefore, certainty regarding the position of the particle, according to Heisenberg's principle, means complete uncertainty regarding its momentum and reciprocity. Now for Heisenberg, it is measurement. And this has always been the leitmotif with Heisenberg and his great mentor, Niels Bohr. It was the act of measurement which was basically at fault. It was not possible to do the measurements with sufficient accuracy. This did not reflect a fundamental issue in knowability. Can you see how critical this would be? If we say that there's something which is unknowable, it's quite basic. And it is this issue of knowability and observation which has been at the center of quantum mechanics, really from the 1930s onwards. And it is precisely this issue which is of critical importance to us, because it brings to the fore the nature of the mind, the knower. And it leads us to the main topic of this conference, which is observation in quantum mechanics. Now, the issue of observation in quantum mechanics and the nature of the observer, in other words, the experimenter, was an issue which was debated and fought with the savagery of jungle warfare by the greatest physicists of the age. I think it's fair to say nobody really agreed with anybody else. And so the greatest minds of the 20th century have tried to answer the question of whether quantum mechanical theories have merely implications for observation, or observation, or if they have fundamental implications for the observer. There are a series of schools in the matter. The orthodox interpretation is called Copenhagen interpretation, is that of Niels Bohr, of Heisenberg himself, and remains, I would say, mainstream nowadays, although it is dwindling as far as the number of adherents are concerned, because the data is piling up against it. This school asserts that the problems we encounter in defining the status of the observer in quantum mechanics, the impact the status of the observer has on the phenomenon observed and on measurement, are all due to the problem of measurement at that level. They are not due to the fact that, for instance, the observer consciousness might be non-material. For Neumann, Fritz Rondon, and Wigner, some of the greatest minds of the 20th century, are of the opinion that the observer is necessarily non-material. It's a necessary corollary in quantum mechanics of the act of observation. For Neumann, to give you an idea, he is the creator of modern computer science. He's also the creator of game theory, one of the greatest mathematical minds who ever lived. Great Hungarian physicist. So the quantum paradoxes appear with perhaps one of the most famous quantum paradoxes there is, the double-slit experiment. Einstein had established that light can behave either as a particle, a photon, or as a wavelength. Both descriptions are appropriate. But what is really puzzling, and this is known as the double-slit experiment, is that in function of what the observer chooses to measure, light behaves as a particle or as a photon. It seems as if the intention of the observer influences the observed phenomenon. If the observer, I'm sorry, I must make sure myself not to disappear. If the observer, for instance, chooses to measure light as a wave, that act of measurement suddenly brings out diffraction, which is a typical wave-like phenomenon. We have a case of diffraction in the background. If, on the other hand, the observer chooses to measure particle-like features of light, that choice of the observer brings out particle-like behavior. It seems as if the intent of the observer, in other words, the physicist, the experimenter, affects how the phenomenon manifests. And there's nothing in classical physics which is even remotely close to this. So this seems to intimate, or to imply, a very close link between the observer and the observed phenomenon. And all the debates in quantum mechanics have hinged about what the nature of this link is. Now basically, what happens when something which is being measured manifests as a wavelength, as a particle, is what is known technically as wave function collapse. Every particle in quantum mechanics is described by a function. It's a mathematical function which describes all the possible states of that object. And according to quantum mechanics, it coexists in all of these possible states until a measurement is made. At the point at which that measurement is made, the particle, and you'll forgive me for the use of the term, chooses to manifest as a particle, as a wave, at one level of energy or at another possible level of energy. Until measurement has occurred, all you can deal with is a wave function which describes the totality of the possible manifestations of a particle. And the interpretations in quantum mechanics hinge on how this wave function is understood. The Copenhagen school, which is basically the dominant school, that of Niels Bohr, that of Heisenberg, as well as von Neumann's school, both consider that this wave function understanding, the totality of the possible states of a particle, is indeed the dominant way of understanding particle behavior, and they merely disagree regarding what causes a wave function collapse. In other words, what causes a particle to manifest as a particle or a wave at energy level S2, S1, or whatever. There are other schools of thought which de-emphasize wave function collapse, which we shall not talk about here. Everett's multiple universe hypothesis and so forth, which are very far away from our topic. Some are discredited. David Bohr's hidden variable synthesis is basically discredited nowadays. So if what we are dealing with is, if you wish, a packet of possible states for a subatomic particle, and what determines the manifestation of one of those states is a wave function collapse, the question which arises is, what causes this wave function collapse? And this is where the schism, if you wish, in quantum mechanics has occurred. The Copenhagen school considers that it is measurement with the intrusion measurement implies which causes this collapse. But von Neumann, London, Wigner, and pretty much everyone else consider it is not measurement. It's the actual consciousness of the observer which causes the collapse of the wave function. And this debate has been ongoing since the 1930s. I reassure you, the most difficult part is behind us. It starts to get a little bit more manageable now. And as we talk about it, I hope these very strange concepts will become more evident. Now, I would say that it is precisely this disagreement which is critical for us. Because if the collapse of the wave function is caused just by the act of measurement, by interference with a subatomic system, that is basically trite. It's not terribly meaningful from our standpoint. If, as von Neumann believes, it is a fundamental feature of subatomic reality, it is the act of knowing a subatomic particle which causes that subatomic particle to manifest as a wave, as a particle with one energy level with one other. This is of fundamental importance for us, certainly as Buddhists. This is a massive vindication of the Indian schools of philosophy. Not just Buddhism, but also Vedanta. And therefore, we shall enter into a bit more detail on this topic. One has to always address the position of one's opponent first, and therefore we shall first talk about the Copenhagen interpretation of the role of the observer, as held by some of the two greatest minds of 20th century physics, the Danish physicist Niels Bohr and the German physicist Werner Heisenberg. Both considered that the transition from the possible to the actual, from this packet of possibilities to an actual particle or wave of a given energy, depends on the act of observation. It does not depend on the act of registration of the result by the mind of the observer. It is the act of observation with, let us say, for a subatomic particle, maybe a bubble chamber, who knows, maybe an electron microscope, various apparatuses which actually interferes with the state of the particle and causes this packet, which we call the wave function, to take a value. Now this is the Copenhagen interpretation. But the act of measurement disturbs things, if you wish. This, however, is not at all von Neumann's position. And von Neumann's position, I would say, is mathematically and physically much more difficult. It is very problematical because it implies a complete reassessment of our fundamental worldview. Von Neumann starts by analyzing, he dedicated a huge book just to this topic, I spare you the details, the system observed, which is subatomic, set of particles. And he subdivided this into one system observed, a measuring instrument, and an actual observer. And he pointed out that Bohr and Heisenberg's understanding implied that the measuring instrument and the actual observer be seen as one. Then when they are seen as one, you cannot make a differentiation. And you are in the position of having to say, it is actually the measuring entity which causes the collapse of the wave function. But if you move what he called the von Neumann cut, which is the division between the observing complex and the observed system, backwards, after all, the measuring instrument participates in the quantum phenomenon. This only leaves the actual observer as possible source for the wave function collapse. And von Neumann considered that any material entity, by the very fact it was material, could not cause the collapse of the wave function, since it was not different in kind from the, let's say, the neutron, the neutrino, the electron, whatever, which was being observed by its means. It itself actually can be written as part of the wave function. Something which was removed from the wave function had to cause the collapse. And that which was removed from the wave function was the actual observer, which therefore, in von Neumann's formalization of wave function collapse, is necessarily non-material. Since if the observer is material, the observer can be subsumed, as here, in the system observer. Then you would have nothing to cause a wave function collapse. Do you understand his point? What he is saying is everything which is material can be described by the so-called wave function. And this wave function collapses. We know it collapses. So it is something which is not material, which causes a wave function collapse. What is non-material? The physicist. In this case, the mind of the physicist. The mind of the experimenter. So in von Neumann's formalization, mind is necessarily non-material. If you wish, in a simpler example, which is only very approximate, because we're not dealing with subatomic phenomena. Imagine you wanted to measure the temperature of melting iron. And your measuring instrument is a thermometer. And then with the eye, one observes, let's say, imagine that melting iron is melting at 2,500 degrees, let's just imagine. You observe this, and this data is transmitted to the brain. All of this is material. All of this can therefore be described by one wave function. The collapse of, let's say, this wave function cannot be caused by this, because this is material. Therefore, we need something removed from this, removed from the brain, which is able to cause the collapse of all of this as a wave function, all of this as a wave function, and that which is removed from the brain has to be non-material. If it were material, it could be described as part of the wave function. And this is of extraordinary importance for us. Because if von Neumann's position is correct, and we're speaking of a position which has the endorsement of some of the leading quantum researchers, then there is proof not only that the mind is non-material, but that the mind must be non-material. After that, it is up to biologists and others to come up with mechanisms for us. That doesn't concern us. They haven't come up with mechanisms yet, but they're going to have to. And the data has been piling up, especially since the late 1960s. We'll talk about some very recent data from Australia, which makes a very strong case for von Neumann's hypothesis. So Henry Stapp describes this rather aptly when he says that von Neumann moved the cut step by step until at last the entire physical body of the observer and of all observers and of everything else was shifted to below the cut and described in terms of quantum mechanics. Then the psyche, in other words the mind of the experimenter, is shifted completely outside of the physically described world, which implies that the mind of the observer is necessarily non-material. If it is not non-material, it cannot cause the collapse of the wave function. And the collapse of the wave function is a given. We know wave functions collapse. Then, this is as close to the sharp wooden stake driven in the breast of the vampire of materialism as it gets. It doesn't get much closer than this. This is the closest you will get to a demonstration of the non-material nature of mind. And it led Fritz London to state the apparent point of departure of the theories, in other words, Newtonian mechanics, the idea of an observable world totally independent of the observer, was a vacuous idea. Strong words indeed. The formalism of quantum mechanics implies a well-defined theory of the relationship between object and observer, a relation quite different from that implicit in naive realism. And this was written, believe it or not, in the 1930s. The book was translated in the 1980s in English, London wrote in French. And as Mondon adds, and this is a very powerful critique of Heisenberg's understanding of the act of measurement as causing the collapse of the wave function, a coupling with a measurement, with a measuring device, is not yet a measurement. It's a very powerful statement. If you have a subatomic particle, and you actually plan on observing its characteristics, and you couple it with a measuring device, that coupling with a measuring device is still not a measurement. It is the moment the consciousness of the observer observes the data that you can speak of measurement. And this is a distinction Heisenberg does not make. We know to I skip the essential role played by the consciousness of the observer in this transition from the mixture to the pure case. The mixture is basically the wave function with all its possibilities. The pure case is the collapse of the wave function, or what modern physicists know as a reduction of the state vector. So you can see here that really since the 1930s, one of the central philosophical debates in modern physics, in quantum physics, has been the nature of the mind. Everyone agrees on the theories, there's no disagreement. All the physicists agree that I extend a p greater than equal to h and 2 pi is general agreement. Nobody agrees on the meaning of these theories. There are two broad camps. The first which say it can all eventually be reduced to our meddling with very subtle particles. And the other camp which says something more fundamental is at work here. It's the actual act of consciousness which causes all of this. This act of consciousness is necessary in material, otherwise it will be part and parcel of the phenomenon observed. Can you see how far-reaching this is? And that's why I told you to get a big cup of coffee before this conference. Numerous paradoxes were actually developed on this basis. The most famous ones are Wigner's friend. These are paradoxes involving the collapse of wave functions, which clearly intimate that what causes the collapse must be the non-material mind of the observer. In Wigner's paradox, you have to imagine that you have two physicists, two friends, doing an experiment on a particle. Now, one is inside the lab and one is outside. The one inside the lab is observing the system and has done whatever measurement he plans on doing. And obviously, by observing it, or Heisenberg would say by doing the measurement, the wave function has collapsed. So whatever it was has manifested, let's say, either as a particle or as a beam, a certain energy state. But his friend outside the lab has not done the measurement. So for that friend, the wave function has not collapsed. So we have a situation in which, if it is indeed the act of measurement which causes the collapse of the wave function, we have simultaneously a collapsed and non-collapsed wave function. In other words, a paradox. And the question is, how do we resolve Wigner's paradox? Wigner himself pointed out that if this were the case, the same physical reality, one particle being observed in the lab, would be described by two different wave functions, one which had collapsed, the other which had not collapsed at the same time, which is obviously impossible. And therefore, that it has to be the consciousness of the first observer in the lab which causes the collapse of the wave function. So Wigner's paradox lends a lot of support to von Neumann's hypothesis that it is the consciousness of the observer which causes the collapse of the wave function. I told you I would stretch your minds, and I think I may be looking at your expressions. Do you have any questions before I go any further? Yes, please.
One that comes to mind immediately, because it's a pretty superficial question, probably. If B is outside the library, outside the laboratory, then he is not performing the measurement. And therefore, surely the connection with the argument is irrelevant. In other words, how does he know that the wave function has not collapsed?
He wouldn't know. How could he know? He wouldn't know.
Well, how do we know that to him it has not collapsed?
That is even more complicated if you have a third observer. That is even more complicated. But the basic question is, what causes this collapse? Then the stakes are very high, because if it actually is the mind which causes the collapse, that means that there is an intimate relationship between mind and matter, which is something which has been denied by all of modern science. So intimate that just observing something can cause it to change. Then, if that is not the case, we return to the classical model. So because the stakes are very high, people have basically, or physicists, have been trading paradoxes since the 1930s. Much of the data at present confirms, especially since the late 1990s, von Neumann's hypotheses. It's become quite embarrassing. And I'll show you how embarrassing it has become. A leading physicist has actually declared that the universe is mental. In Nature magazine. And if you've heard of Nature magazine, it's one of the 2 leading science magazines in the world, general scientific magazines. Then obviously for us it is difficult to understand these arguments, but what I'm hoping to do is to make it clear that we are at a point where a rational, modern, 21st century Western